Welcome back to our series on building a linear regression model inside of Python using sklearn. So in our last video, we basically built an instance of our model. So we first got our data set, we split it into a training state and then a testing state. We created an instance of the linear regression model. We fit our data to that model. And then we explored some of the outputs, interpreted basically what they were meaning. And then we saw how to take a single prediction. And then we also saw how to do multiple predictions. And we realized that with this one, this is where we were basically testing our data set. And so now that we have a test instance, we want to basically evaluate how well did our model do. Now, this is going to kind of be broken into two sections. I'm also going to leverage another library, the stats model API library, just because they have, I think, a little bit better of a scenario when it comes to summarizing the performance of a model. And they have these wonderful methods where it creates a nice detailed summary of how the model performed. So the first thing that we're going to do is we're going to actually create a new instance of the linear regression model, so that way we can leverage those particular summaries in our tutorial. So the first thing I'm going to do is I'm going to create a new variable called x2, and then I'm going to do add constant, and then pass through my my x variable. And then, if we go up here, that's really just our input. And then from here, what we're going to do is we're going to create a new variable called model. We'll call our stats model API library. We'll call the OLS, so ordinary least squares model, and then y x2. So here's our output, here's our input, and then we need to do estimate. So basically fit the model. This error comes up. I think it's just because of the version of NumPy that I'm on. On my work computer, it doesn't have that problem. So just disregard that. It's fine for this point. Once we have this, it really makes sense to do a confidence interval. And so really with a confidence interval is, why do we do this? Well, we have to recognize the fact that we're really only taking a sample of the population of all the potential prices that oil and Exxon have had over their entire life. And so because we're not taking the entire population itself, we can't say with 100% certainty that the true coefficient exists, basically in the interval that we're going to define below. So it could exist in there or it couldn't exist in there, but we can't say for certainty. And so we use these intervals to say, hey, well, with 95% confidence, we are saying the true coefficient exists somewhere in this particular range. Now, with the particular model that we have, all we have to do is we just call the confidence int. And what this does is this is our confidence interval for our constant. Most time we can disregard the constant one. The one that I'm really concerned with is the oil price. So I'm saying with 95% confidence that my coefficient could be 0.21 or 0.24, somewhere in between that. If I want more confidence, I'm going to have to do a wider range. And then if I want less confidence, I'm going to do a more narrow range. So it's really here to kind of help say with some level of confidence that, hey, our coefficient exists in this interval, but we can't say for sure, but we can say with 95% confidence. And that is just really boiling down to the fact that we're working with a sample. We're not working with the entire population. So we can never say with 100% confidence that the coefficient that was estimated was true. That's the important part that we have to take away from this. We can never say with 100% certainty that that coefficient that was estimated was true because we're only working with a sample. We're not working with the entire population itself. Okay. So now we're going to go on to the hypothesis testing, the fun stuff, right? Yeah, sometimes. It's important. If you skip this step, it obviously sets the stage pretty poorly. This is what I skipped in the last video, so that's why I'm covering it now. Okay, so with the hypothesis testing, basically what we're going to do is we're going to have two hypotheses, a null hypothesis and an alternative hypothesis. We want to disprove our null hypothesis. So basically we want to reject our null hypothesis and we want to accept our alternative hypothesis. Now, our null hypothesis in this situation is there is no relationship between the price of oil and the price of Exxon. So in other words, what we're saying is the coefficient equals 0. So our coefficient up here in our model, it really equals 0. So we want to reject this hypothesis. We want to say, actually, no, it does not equal 0. So in other words, we want to accept all alternative hypothesis, which is saying there is a relationship between the price of oil and the price of Exxon. So again, to reiterate, if we reject the null, we are saying there is no, if we reject null, we are saying there is a relationship and the coefficient does not equal 0. If we fail to reject the null, we are saying there is no relationship and the coefficient does equal 0. Now, lucky for us, this is really easy to calculate. Again, we're going to take our model and we're going to look at the p-values and then we're going to interpret it. Okay, so we can disregard the constant one. What this one is it's saying it's pretty much 0. It's a really, 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 really small, small number. And so to kind of interpret it, the p-value represents the probability that the coefficient equals 0. We want the p-value that is less than 0.05. If it is, we can reject the null hypothesis. In this case, if you look right here, the p-value for the oil price coefficient is much lower than 0.05. So we can reject the null hypothesis and say that there is a relationship and that we believe it to be between oil and the price of Exxon. So all we're saying is there is a relationship and we believe that it is between oil and the price of Exxon. So at this point, it's basically saying the model is working to a certain extent. Now, or at least it's saying there's a relationship. But now we need to test, how well is our data actually fitting the model? That's another important thing that we're caring about. So there's a couple different metrics that we can look at. What we're going to do is we're going to see what did our model predict, and then we're going to compare them with what the actual values will be. These are what we call residuals. So we're going to see what the model predicted and what the actual value was. Now, most of the time there might be an error. And what we're going to do is we're going to take all those errors and we're going to try to put them into different metrics and basically try to answer the question, how well is our model performing? There's a couple different metrics we can calculate. The first one is the mean absolute error. With this one, this metric gives an idea of the magnitude of the error, but no idea of the direction of the error. So all it's going to do is it's going to say, take the error and then divide it by the number of values, and it's going to say, well, on average, you're making this amount of an error, but it's not telling me if it's too high or too low. And so a more popular metric is the mean squared error. With this one, because what it's going to do is it's going to punish larger errors. This one kind of treats them all the same. With the mean squared error, because we're squaring something, if I'm squaring a large number, it's a really large number. So this one's going to punish those large errors. It's saying, hey, if you screwed up and you screwed up bad, you're really going to get punished. I don't want to give you any of that. So even if you make, 5 really good ones, but you make 3 horribly horrendous ones, it's going to punish those larger errors. Now, another popular metric is the root mean squared error. That's simply the square of this one. The square root of the mean squared error. This one's more favored because it allows us to interpret the output in Y units. Okay, so let's take a look. Let's calculate each one of these metrics. And so the first one is model MSE. And then we'll do the squared error. We'll do the Y test. And then the Y predict. And then I might just be changing some of these. And then absolute, Y test, Y predict, and this is going to be MAE, and then model RMSE. And then that will equal math. We'll take the square root method and then pass through the model MSE. And then we need to display the output. So we'll say print. MSE is equal to brackets. Colon dot, and then we'll do 3. I think 3 is what the one needs to be. Format, and then model MSE. And then this will be MAE, and then this will be RMSE. And then I'll change that to MAE and then RMSE. Okay, so the MSE, the mean squared error, is simply 38.8. The mean absolute error is simply saying 5.05. And then the RMSE is 6.23. So basically we're saying that on average we're making an error of 6.23. Okay. So now that we've done that, let's talk about R squared. So why do we use R squared? What does it, kind of provide us at the end of the day? Really what it's doing is it's providing us a goodness of fit, or how well our data fits the model. And so generally, if the R squared is higher, it means the data better fits our model. Where if it's lower, it means it doesn't fit our model as well. You're going to find R squared is subjective sometimes, and we'll find there's certain situations where you really have to understand kind of what you're looking at and really what it is. Funny thing that you need to know is that the R squared is simply the square root of the correlation. That's all it is. Or sorry, not the square root, the square of the correlation. And so that's really all we're kind of calculating down here. Now, a lot of metrics and like a lot of libraries and stuff like that, you can just calculate it yourself and stuff like that. But for here, we'll take the R squared, and then we'll take the R2 score, and then what we'll do is we'll call the Y test, and then the Y predict, and then what we'll do is I'm just going to copy this one just because it's easier. And then we'll say R squared. And then we'll do 2. And so it's 0.36. What this is telling me is basically our data explains 36% of the variance. Is it good? Is it bad? That's kind of up to interpretation. It really kind of sometimes depends on the domain that you're working with. Sometimes, especially like, for example, in psychology fields, it's very normal to have low R squareds because you're dealing with things like human psychology, which have a lot of variables that can impact of it. So even with things like stocks, I mean, I've seen things where it's like if you get an R square of 0.40, that's considered good. It's really all about the domain that you're working in. But at this point, all we need to say is that it's simply telling me that the R squared is 0.36. And so basically we can explain 36% of our variance with the data. Personally, I think that's pretty good for a stock model. With stocks, there's a lot of variables that are playing at hand. And then we have to understand that, well, if you want to increase your R squared, well, how do you do that? Well, one way is you just add more features to the model. So you just add more columns of data. The problem is it's going to always go up. That doesn't necessarily mean that those features that you added to the model are actually any better for the model. And so another metric that is calculated a lot of times along with the R squared is the adjusted R squared. With the adjusted R squared, we basically penalize you for more complex models. So if you keep adding features, we know that your R squared is going to go up, but that doesn't mean it's necessarily benefiting your model. So the R squared will only increase if the columns that you're adding are actually helping the model more than just random chance, and it will decrease it otherwise. And so that's why sometimes you'll notice that your R squared is actually lower. Your adjusted R squared is lower than your R squared because it's penalizing you for your particular model. So that's the R squared metric. Again, all it's doing is it's telling how well does our data fit this model. And in this case, we can explain basically 36% of our variance with our data. It might not sound like a lot, but I think for a stock model, that's actually relatively well. Like I said, I've seen other papers and stuff like that. If they got 0.4, they were static. Even things like psychological fields and stuff like that, it's very common to have very low R squareds because there's usually a lot of variables at play. Okay, so now that we've done that, let's just do a couple more things and then we'll finish off the video. So this is probably going to be the last video of this series. I could probably break it into 2 videos, but I think it's just better to finish it out here. The first thing that we're going to do is we're going to print out our summary of the actual model. So again, this is using the stats model in this particular example. So up here, we were using the sklearn to calculate certain metrics. But here I'm going to use the stats model again. And this is why I love the stats model. It gives you this beautiful little thing. Look at this. It's perfect. It just summarizes everything so well. The first thing, dependent variable, the model that we use, the method, the date, time, number of observations, residuals, and then the model itself. And so really cool, or sorry, degrees of freedom. So basically just how much we were kind of giving freedom to, which how many variables. We get our r squared again, so that's the 36 up here. Our adjusted r squared. These are pretty much identical because we don't really have a complex model. We have a very simple linear regression model, so that makes sense. Log likelihood, F statistics, probability, all that kind of stuff. And then we get our little output, our coefficient for each variable, and then our intercept, the standard error, the t-value, and then the p-value, and then our confidence range here as well. And so really, this is just kind of validating, again, that this particular attribute is actually playing a significant role in the actual model itself. So the larger these values, the larger the t-value is, the better, and the lower the p-value, the better. And then it also does a nice thing with skew and kurtosis. So again, everything seems to be well within normal ranges. So overall, it looks fine. I'm kind of happy with what we're seeing. So this is a great way to do a nice little summary really quickly and make our lives 10 times easier, because otherwise we'd have to compute all of this with the sklearn library, and they unfortunately don't have these nice little methods like that. So this is really why I use the stats model API library, just because it makes it so much easier. Okay, so the next thing that we want to do is we'll just plot the residuals. This is really just for me to kind of help say, do our residuals look normal, in the sense of, do they have like a normal distribution? So what I'll do is I'll call y-test minus y-predict. And then what we'll do is we'll call the histogram function. Again, I don't want any grids. And then color, we'll change it up. We'll do equal to royal blue. And then from here, we'll do a plot, title, model, residuals, and then we'll show it. Okay, apparently it did that. Great. So here's our residuals. So basically, how many times were we off by this much, how much we were off by this much, and the frequency of it. And for the most part, it's normally distributed besides this little thing right here. So that would be kind of interesting to see kind of why it tends to kind of looks like it's making more negative errors than it is right here. So that's kind of interesting. But for the most part, it looks relatively fine. And again, looking back up here, there was nothing that was kind of like, something's going wrong. We need to, change something or things along that nature. So for the most part, everything seems fine. So now that we've done that, let's actually like plot our line on a graph. So we'll take our scatter plot and then we'll actually put a line on it. So this is going to be a little bit more on the lengthy side, but that's okay. So we'll do plot.scatter. And then we'll again do our x test and our y test. And then we'll do the color. And then equals Gainsborough. This is like light gray. We want a label for our legend, and this will be our price. And then I will do, no, not like that. And then we'll do plot. Plot, and then we'll do x test, y predict, color equals royal blue, and then line width, so the length of our line we'll do equal to 3. Line style is going to be just a solid line. And then label is regression line. Okay. And then we'll also do a title. And then what we'll do is linear regression model, Exxon versus oil. And then, oops, and then we'll do X label. And then that will be oil, plot.y label, Exxon Mobil, and then what is it? Plot.legend, and then plot.show. And then I want to make sure that that's still lined up with what we did up here. No, see? Oh, it's fine as long as the laxes are good. Oh, what's wrong? Okay, so that's good. So we have our Exxon Mobil, our oil price, and so it's a scatter plot. Really, this is basically our line, and so this is a nice little label where here's our linear regression line, here's our price. We could also add a couple other things. So maybe we wanted to have, what is it? The coefficients below or something like that. So I'm actually going to skip over that for right now, just for time instances. I really wanted more to just show how to actually plot the graph. But when you get this document, I will have this code filled out for you. It's basically what we were doing up here. That's really basically all we were doing. I was doing a little bit more fancier. I was bolding certain parts, but I'll save that for, something else. So this is how we would make our linear regression line on top of our scatter plot. Again, you want your line to pop, so that should be more of a brighter color. Your prices, that should just be more gray, something that kind of stands in the background. And we're trying to say, hey, this is how it's fitting into our model. So really cool. I like that. The final thing that we're going to cover is how to pickle our model. When we pickle our model, we're basically saving it so that way we can use it in a future instance. But more importantly, it takes all the training instances that we had done before and all those wonderful little parameters, and it saves it for us. This is very useful because when you're training very, very large models, the last thing you want to do is just to make a single prediction is run the entire model again. You would simply like to open the model and then just put in a regression and you're good to go, right? Or sorry, not put in, but put in a predicted value and then see what comes out, right? That's ideally what we would like to do. So with pickling, we save our model for future use, and basically we're creating a byte stream. And so to do this, we're going to say with open, and then we'll do brackets, and then we'll do my linear regression, and then we'll do .sav, and then we want to make sure that we save it. We can write to it, and then we'll do an alias as f, so that will be our file. And then we'll say pickle.dump. Keep in mind, I did import the pickle library. Otherwise, we can't do this. Regression model, and then f. So dump my regression model in this file. And once we've done that, we're going to open it back up. But in this one, what we're going to do is we're going to create a new instance of our model. And so we'll say regression model 2, and that will equal pickle. But this time we're going to do load. And I'm going to delete this and say load it from that file. And that's it. And then once we have our new loaded model, let's make a prediction. So let's pass through 67.33. What's going wrong? Oh, that's what I should definitely say. Okay. Keep in mind, I want to make sure I can read it, not write to it. So all we did is we saved our model, and then we loaded it back into our little Jupyter notebook, and we made a prediction. And then basically this is what it outputted to us. So there you go. that's basically how you save your model, and that's how you open it back up again to make all your fun little predictions. But this is great. I mean, this is so important because obviously, like I said, some models take days to train, and the last thing you're going to want to do is retrain it every time you want to make a prediction. You just want to simply take your trained model, pass through some predictions, and you're good to go. That's the ultimate goal. So with that being said, though, that is the conclusion of this video, and more importantly of this series. So if you have any questions about what we covered today, you know, the linear regression model in general, you know, why I approach certain things along that nature, please put them down in the comments below. And then if you could, please make sure to like the video. And then if you're not already, please make sure to subscribe to the channel so that way you get regular updates. Hopefully you guys found this video a little bit more detailed behind it. Again, I want to make sure you're getting the right information. And I know in the last video, I might have glazed over some stuff or I didn't kind of go into detail, but hopefully now, you know, you can better understand the results you're getting. You can better evaluate your models and things along that nature. I'll make sure to put up this document as well so that way you guys have access to it. Probably gonna do a couple more formatting stuff and things along that nature. But overall, hopefully you just have a better idea of what a linear regression model is and how we use it in machine learning. You know, these aren't perfect models. And, you know, I'm not going to say you're going to get rich overnight, you know, using this with the stock market. In fact, they tend to perform pretty poorly. But I think a lot of people, this is how they understand these types of models because it's something so applicable. Not going to necessarily say it performs well, but I think it gives you a good idea of what this model is supposed to be doing and really why we're using these models with financial products. A lot of times you'll see this used with forecasting a ton because it's very easy to build. It's very easy to interpret. You just want to make sure that you're evaluating it and you're understanding what kind of model you're using. And then hopefully you found the process of actually exploring the data and loading the data useful too. I want this to be more realistic in the sense of very rarely will you ever get a data set that is perfect. You have things wrong with it. And so ideally, I want you guys to understand the process of cleaning your data and then more importantly, exploring your data, actually taking the time to look at it and making sure that there is something there and that you understand how it looks and what you might need to do in order to make sure your model performs better. So thank you again for watching, guys. The next series, we're going to do classification. So really cool stuff. I'm looking forward to that model, but we'll see you in the next video.